In this example, we are going to describe the solutions to polynomial inequalities. So here I'm given a particular function, f of x is equal to x squared plus x minus 6. This is my function. And over here I have the graph of my function. What I want to be able to find is when this function is equal to 0, I want to know when this function is greater than 0, and I want to know when this function is less than 0. We eventually just want to be able to, in the next couple of pages here, we want to just be able to be given a function and solve when it's either less than 0 or greater than 0, or maybe it's less than or equal to or greater than or equal to. But we want to be able to solve these inequalities. So the first thing we want to be able to do in the steps here that we'll see is you want to just, in order to describe when it's less than or greater than 0, the best thing that you can do is just find first when it's equal to 0. And here I give you the graph. And we know, just by looking at this graph here, it's going to be equal to 0 at, right here, 1, 0 is x equal to 2 and x equal to negative 3. So when is this function equal to 0? Well, those are the zeros of my function. That's x equal to 2 and x equal to negative 3. Now again, if you weren't given the graph, how would you find that algebraically? Well, we see that x squared plus x minus 6, this can be factored into x plus 3 times x minus 2. So since this factors, we can then set each one of these factors equal to 0, and we get x equal to 2 and x equal to negative 3. Now, when I want to know when this function is greater than 0, right? In other words, I want to know when my function is positive. If it's greater than 0, it's positive. The outputs are positive. If the outputs are positive, then I'm talking about this region up here. This region up here, I want to know for what values of x is my function above the x-axis. Well, it's going to be above the x-axis up until it's not above the x-axis. I know that sounds weird, but really the point of finding these zeros first is because that is the point. When it stops being in this particular function, that is the x value when it stops being positive and it starts after that to be negative. So that's why it's essential that we first find the zeros, because around these zeros, that's where all the action's taking place. So just by looking at this graph, I see here that this function is positive all the way from all the values to the left of negative 3. Right? So just looking here, I see that my function will be greater than 0, starting at negative infinity, and up until negative 3. But I'm not including negative 3 because if you look at negative 3, that's when it's equal to 0. So it's not greater than 0 when it's negative 3, it's equal to 0. However, it looks like we also have values over here to the right. My function is above the x-axis all the way over here to the right, and those are x values starting at 2 and going on forever. So this would be 2 to infinity, and we want to be able to put these together so we say with a union. Now, if I want to describe when the function is less than 0, right, well, up here we see that it is greater than 0. It has outputs that are positive. At negative 3 and 2, we see we have values that are equal to 0. When we're trying to describe when our function is less than 0, what we're looking for is when our function is below the x-axis. So it looks like, we're still finding the zeros because that's where all the action's taking place. That's where it goes from being positive to negative. And we see here starting at negative 3 but not including negative 3, our function is entirely below the x-axis, and then it stops being entirely below right here at negative 2. So if I wanted to write that in interval notation, starting at negative 3 but not including negative 3 would be negative 3 up into the value of 2. And we're not including 2, again, because at 2, if we wanted to include 2, this would have to be less than or equal to. Now this is nice because we were given the graph. What if we're not given the graph? What can we do? Now we're given another polynomial inequality to solve. We are told that our function is x squared plus 8x plus 15. and I want to know when this function is greater than or equal to 0. We're not given the graph, so you can't just cheat and figure that out. However, we're going to think about why the graph was important, what were we considering when we were using the graph. And the first thing that we were considering is not when it was greater than 0, but when it was equal to 0. That's the first thing we find, because it's around those zeros where the function's either going to be above or below that. So the first thing I'm going to do is I'm going to find, let's first find the zeros. In other words, let's find f of x equal to 0 first. So I'll have x squared plus 8x plus 15 equal to 0. Now this is a quadratic equation. We have a couple ways that we could do this. We could solve this by factoring if it's factorable. We could use the quadratic formula, or we could complete the square. I know that this can factor into x plus 3 times x plus 5. If you're unsure of how that factors, then you can go back and look at my factoring podcast, or you could just use the quadratic formula. So now we set each one of these factors equal to 0, and we get this is -3, and x plus 5 equal to 0. That happens when x is equal to -5. Right, that's great. We found values for when this is equal to 0. So what we want to do now is we want to make a number line, because it's not necessarily these values that we're looking for. We're looking around these values. So I'm going to put -5 and -3 on a number line. And what I want to do is I want to know what's happening in between -5 and -3. I want to know what's happening to the left of -5 and to the right of -3. So in order to do that, what I'm going to do is I'm going to choose a value over here. It doesn't matter what it is. I'll choose a value in the middle, and I'll choose a value to the right. So what I decide to do, I'm going to do on the next page, I'm going to plug in let's say -8. I'm going to plug in between two numbers here, in between -5 and -3, I'll plug in -4, and something larger than -3, any value larger than 3, let's make it easy, let's plug in 0. So on the next page, I'm going to plug in -8, I'm going to plug in -4, and I'm going to plug in 0. What am I going to plug that into? I'm going to plug that into this function here, because I want to know, when I plug in -8, is my function greater than or equal to 0? I know it's not equal to 0, because that happens at -5 and -3. So I'm going to plug in -8, and I'm going to find out whether or not this function is greater than or equal to 0. If it is, I will shade this. I'm going to plug in -4 into my original function. Does it satisfy this inequality? Is it greater than or equal to 0? If it is, then I know those numbers in between -5 and -3 will satisfy that. And finally, I'll plug in 0 into my original function here. If it's greater than or equal to 0, then I know that that also will be greater than or equal to 0. So let's do that on the next page. On this page, I already have some work done for us. We see here up top, I have my original function. The function was x squared plus 8x plus 15. We found that that factored into x plus 3, x plus 5. When we go and plug values into our function, it doesn't matter if we plug it into x squared plus 8x plus 15, or if we plug it into x plus 3 times x plus 5. These two expressions are identical. They are the exact same thing. So on the last slide, I told you we would be plugging in -8. We'd be plugging that into the function, and we want to determine whether or not that's greater than or equal to 0. So I took my function, and it's going to be equal when I plug in -8. This is what it's going to be equal to. I evaluate that, and I find that when I plug in -8, I get positive 15. So you need to ask yourself, does that satisfy this inequality? At f of -8, is that greater than or equal to 0? Well, I plugged in -8. I got positive 15. So that is greater than or equal to 0. What that tells me is that starting at -5 and going to the left here, those values are going to satisfy my inequality. Now I am going to just stop here for a second and say, well, is negative 5 going to be included or not? And I probably should have mentioned this on the last slide. But since we're talking about greater than or equal to, we found negative 5 and negative 3. Those were the values that satisfied this function equal to 0. So these values of negative 5 and negative 3 for sure are going to work. So you might want to just mark those with closed circles right now. Those are definitely going to work. Right? Again, because this is greater than or equal to 0. So these values were equal to 0, they're going to be included. Now I'm going to, you'll see here that I plugged in, I plugged in negative 4. That was my representative from this middle group. I plugged in negative 4. I evaluated my function at negative 4 and I got negative 1. That is a negative value. That is not greater than or equal to 0. So since that's not greater than or equal to 0, this is not going to work. This is not going to work. So I am not going to shade this middle region because it is not, when I plug in negative 4, that's the representative from this group, it was not greater than or equal to 0, therefore we're not going to shade that region. And finally, the representative from this right group here, the values that are greater than or equal to negative 3, I decided to choose one single value. The easiest possible value I could use was 0. When I plug 0 into my function, I find that I get a value of 15. 15 is larger than 0. It is positive. That tells me I'm going to shade all of these values. The last thing that I'll mention here, before we write the solution interval notation, I said last time it doesn't matter if we can plug it into this trinomial or the factored form. Sometimes it's easier just to plug it into this factored form. You can see here underneath, if instead of plugging in negative 8 into the actual function, if I were to plug it into the factored form, I would have negative 8 plus 3 times negative 8 plus 5. And what I see is this value right here, negative 8 plus 3 is going to be negative. Negative 8 plus 5 is going to be negative. Right? I don't even really need to simplify this. I see that this is going to be negative, this is going to be negative. Therefore, a negative times a negative will result in a positive number. Right? Honestly, it doesn't necessarily even matter what the value is. It's nice that we got 15, but all I want to know is when I plug in negative 8, is the function going to be greater than or equal to 0 or less than or equal to 0? Is it going to satisfy? Is it going to be positive? And I find that when I plug in negative 8, it is positive. If we follow this same technique by plugging in negative 4, if I plug in negative 4, I'll get negative 4 plus 3. Plugging it into the factored form, negative 4 plus 5. And what I find is when I plug in negative 4 into the first factor, that's going to be a negative value. When I plug that into the second factor, that's going to be a positive. So I know, even without getting a particular value, I know a negative times a positive is going to result in a negative. Therefore, I know that when I plug in negative 4, it is not going to satisfy this inequality. It's not going to be positive. And following, we could do the same thing down here. Now the last thing I want to do to complete this, and this should be a review, and I'm not trying to fill the screen here with all this work, but we want to be able to talk about the interval notation, what the solution set is. So we see that these are the values here from negative infinity all the way up until negative 5, including negative 5. And we're going to union that with starting at negative 3 and going to positive infinity. Right? So this part right here in this, kind of cramming it in here, but this, an interval notation, would be the solution to my inequality. When is my function greater than or equal to 0? It is greater than or equal to 0 with these values here, from negative infinity to negative 5, including negative 5, and then from negative 3 to positive infinity. Finally, I got this by first taking my function. If I want to know when it's greater than or equal to 0, I need to first figure out when it's equal to 0, because it's going to be the points, around the points where it's equal to 0, that's where all the action's taking place. So I find out that negative 5, negative 3, that's when it's equal to 0, and then that breaks the number line into segments that I'll test a representative from each segment, and that's going to tell me whether or not that segment is included or satisfies the given inequality.